Okay, so we've got the notes for section 4.1 of the chain rule. So this unit essentially also has a lot more differentiability rules. Sorry, it's a tricky word. So the first of them is the chain rule. So the chain rule is used to differentiate composite functions, where you essentially have one function nested inside another function. You can also use it to do curves that have been parameterized, meaning they're written in terms of a third variable t. Okay, so example 1 here. So the function y equals 6x minus 10 is the same thing as 2 times 3x minus 5 is the composite function of 2u and 3x minus 5. How are the derivatives of these three functions related? So let's see here. Well, y prime is equal to 2, the derivative of that. U prime is equal to 3, derivative of that. And the original equation, y equals 6x minus 10, its derivative is 6. And if you notice, these two, the derivative here, is equal to these two derivatives being multiplied together. So it's the product of the two derivatives. So down here, the polynomial is a composite of u squared. How are the derivatives of these three functions related? So we'll do this guy, that guy, and that guy. So u prime is going to be 2u. U prime is going to be 6x. And if u is equal to, we'll do this guy, this original y prime here. He's going to be 36x cubed plus 12x. We get the derivative of that. Now, the thing is, if u is equal to 3x squared plus 1, this becomes 2 times 3x squared plus 1, which is the same thing as 6x squared plus 2. And just like before, if I multiply these two things together, u prime, or y prime times u prime, so 6x squared plus 2 times 6x, that gives me 36x cubed plus 12x, which is what the derivative actually is. So if you take the composite apart and multiply the two parts of the composite, you'll actually get your answer. Down here is the fancy definition for the chain rule. So if f is differentiable at the point u and g is differentiable at x, then the composite function f of g of x, or f of g of x, is given by the product between the two derivatives, f prime, with g plugged back in, times the derivative of g prime. So in this case, that's my u. So this guy would be g prime, this would be f prime, and then I have to plug g of x back in. So this is what it is. Leibniz notation uses dy dx's, so it looks like this, so on and so forth. Okay, so we've got example 3. An object moves along the x-axis, so that's position any time t greater than 0 is given by the function x of t equals cosine of t squared plus 1. Find the velocity. So in this case, our u is going, y is going to be the cosine of u, and u is going to be the t squared plus 1. So when you take my two derivatives, so y prime is going to be derivative of the cosine is the negative sign, and u prime is 2t. So you need to replace my u back in, so this stuff goes back in for u. So y prime becomes the negative sign of t squared plus 1. And so to get the final derivative, I multiply these two things together. So negative 2t sine t squared plus 1. So this will be the velocity, because the velocity is the derivative of the position equation. Down here it talks about the outside-inside rule. This is normally how I think about doing the chain rule. It's kind of, to me, makes more sense. So it tells you the order in which you take the derivative. So you take the derivative of the outside thing first, which in this case is the sine. So derivative of sine is cosine, and then you leave the inside alone. And then you multiply by the derivative of the inside, so the derivative of the x squared plus x. So this would be 2x cosine of x squared plus x plus the cosine of x squared plus x, if you worked out your multiplication. Now, there is a case where you have to do this more than once. So here we've got the tangent of 5 minus sine of 2t. So even though it's not shown, there is an unwritten set of parentheses, and if you've used your calculator, sometimes it'll give you them immediately after the trig function. So here, when I start on the outside, so the derivative of the tangent is the secant squared. Leave everything inside of it alone, times, and now we work the parentheses. So the derivative of 5 is 0, it goes away. The derivative of negative sine is the negative cosine. Leave the stuff inside of it alone. And then finally multiply the derivative of 2t, so times 2. So this, essentially this big ugly string, is your answer. So this 2 is a coefficient, so is the negative, so normally it'd be written as negative 2, cosine of 2t, secant squared of 5 minus sine 2t. So this would be g prime, the derivative of g. If you have a parameterized curve, meaning you have x and y defined in the terms of a third variable t, dy dx is equal to dy dt, so the derivative of y with respect to t divided by the derivative of x with respect to t, assuming that that's not 0. So come over here to example 6. We've got these parameterized equations. So there's the derivative for x, there's y, and there's our bounds. And we're given the point root 2 comma 1, where t is equal to pi over 4. So I need to find the slope, which is dy dx, which is dy dt on top, dx dt on the bottom. So dy dt is the derivative of y, so it's the derivative of that equation. So the derivative of tangent t is the secant squared t. On the bottom, dx dt, derivative of that, so the derivative of secant t is secant t tangent t. So this secant squared, you cancel that out, so this is actually the secant t over the tangent of t. So let's see if this one cleans up. Secant is 1 over the cosine. Tangent is the sine over the cosine. So this becomes 1 over cosine t times cosine t over sine t. Cosines cancel, so 1 over sine t, or the cosecant of t. So that's m. T is pi over 4. So we need to figure out, to write the equation of a line, we need some information. We need the value for m, we need the value for x, we need the value for y. So m we're going to get from here. X and y are actually given to us, root 2 and 1. So the sine, to find m, we'll do this work down here. M is equal to 1 over the sine of pi over 4. The sine of pi over 4 is root 2 over 2. So that becomes like that, which is just root 2. So m is also root 2. So the equation of the line is y equals m x minus x1 plus y1. So distribute root 2x minus 2 plus 1. Root 2 times root 2 is just 2. It undoes the square root. So y equals root 2x minus 1. So that's the equation of the tangent line at that point of that parametric curve. So you've got the power chain rule. So it says, so eventually this is what we've been doing before, it's the power rule. So, but u is not just x anymore. So if you have an exponent, the exponent comes out front, you count down by 1, and then you multiply by the derivative of whatever had the exponent on it. So here in this case, that's what it's going to work. So it says find the slope of the tangent line to the curve. So to get y prime, exponent comes out front, count down by 1, and then you multiply by the derivative of what had the exponent on it, so cosine x. The other way to think about it is this, as far as your calculator is concerned, is the same thing as this, which makes it more obviously a chain rule. So this is the outside, so 5 comes out front, leave the inside alone, count down by 1, 5 sine to the 4th, times derivative of the inside. So now I need to do when x is pi over 3. So remember m is y prime. So this becomes 5 sine to the 4th of pi over 3 times the cosine of pi over 3. So 5, so the sine of pi over 3 is root 3 over 2 to the 4th. Cosine of pi over 3 is 1/2. So this is 5, so root 3 to the 4th is root 3 times root 3 times root 3 times root 3, so which is 3 times 3 or 9. 2 to the 4th is 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. Then there's your half. So that's going to be 45 on top, 5 times 9 times 1, and on bottom, 32. I don't think that reduces. Nope. So the slope of that line is 45 30-seconds. So the second part here, so my equation is this. Is positive everywhere. Now I'm actually going to cheat because this right now is a quotient rule, but I can rewrite it like this with the negative exponent to get that out of the bottom. That 1 there is actually whatever that coefficient is. So now this looks more like a chain rule. So here's y. So y prime, so negative exponent multiplies out front, so negative 3. Leave the inside alone. Count down the exponent by 1. And then multiply by the derivative of the inside, which is negative 2. So this becomes positive 6, negative 3 times negative 2. This has a negative 4th power on it, so it's on the bottom of the fraction. Or this becomes 6 over 1 minus 2x, all raised to the 4th. So it says, show that it's positive. Well, once we have our equation, 6 is always positive. And this, 1 minus 2x to the 4th, will always be greater than 0 as well, because you're raising something to an even power, which always returns positive values. So since you have a positive or a positive, this is always positive, which is more than 0. And that brings us to the end of the section.